In this lesson, we want to learn about adding complex numbers graphically. Also, we'll learn about converting between rectangular and polar forms. Okay, so our first topic of adding complex numbers graphically is very, very easy to do. As long as you understand how to add vectors, you're basically good to go. So we return to our complex plane, which remember is also called the Argand diagram. And basically we replace the x notation here for the horizontal axis with real. We replace the y notation for the vertical axis with imaginary. So if you have a complex number like a plus bi, okay, where again, the a is known as the real part, okay, and the b is known as the imaginary, okay, part. Well, basically I could use this to plot a little point on this complex plane, okay. I'm going to go a units horizontally, okay, and I'm going to go b units vertically. Okay, so if I had something like, let's say, 3 plus 7i, well, the coordinates, if you're thinking about this as working on your regular xy coordinate plane where you have some value here, comma, some value here, well, it's 3, comma, 7, right? I'm just moving 3 units on the horizontal axis. Now it's called the real axis. And I'm moving up 7 units, okay, on the vertical axis, now called the imaginary axis. So 3 units to the right, 7 units up would put me right there, okay? So I would go ahead and label this as the complex number 3 plus 7i, okay? If you wanted to do another one, let's say we do something like -5, let's say minus 4i, okay? So the coordinates there would be -5, comma, -4. So I'm just going 5 units to the left on the real axis and then 4 units down on the imaginary axis. So right about there, let's go ahead and say this is -5 minus 4i. For the purposes of making sure that you understand how to do this, you should pull out a sheet of paper and just make a rough sketch of an Argand diagram. We're going to use it throughout the lesson, so you might want to have that handy. And go ahead and pause the video and try to just graph this guy. Think about where it would be on your complex plane. All right, so hopefully you gave that a shot. This -7 plus 6i, again, the real part's -7, so I'm moving 7 units to the left. The imaginary part is 6, so I'm moving 6 units up. Okay, so 7 units to the left, 6 units up, which would put us exactly right here. Okay, so this would be your -7 plus 6i, 7 units to the left, and 6 units up. All right, now additionally, as you move higher in math, we start to think about graphing a complex number using vectors, okay? And specifically here, we're going to use a position vector or a vector in standard position, okay? So this just means that the initial point is at the origin. If you think about this in terms of a complex number, your origin is going to be at 0 plus 0i, or you could say 0, comma 0 if you want the coordinates, okay? So if the initial point's at the origin and the terminal point would be at this 8 plus 5i, so again, it's 8 units to the right and 5 units up, let's see this position vector graphically. So this would look something like this. Your initial point is at the origin, so right there. Your terminal point is at 8 plus 5i, so again, you're just going 8 units to the right and then 5 units up, and you have a directed line segment or a vector. Okay, so this is how we're going to show this 8 plus 5i when we're asked to graph it as a vector. All right, so now let's use the fact that we can graph a complex number as a position vector to show the sum of two complex numbers graphically. Okay, so we have this 6 plus 5i plus -9 plus 3i. Let's just add this together real quick just so we know what we're supposed to get, and then we'll go to the coordinate plane. So we know we would add the real parts, so we do 6 plus -9. Okay, that's your first step. Then plus, we would add the imaginary parts. So 5 plus 3, okay? And this is multiplied by the imaginary unit I. So what I want to do here is do 6 plus -9, that's -3. And then plus, you have 5 plus 3, which is 8, and then times the imaginary unit I. So -3 plus 8i is your resultant vector. Okay, so let's look at this graphically. And again, you can do this with the parallelogram method or the triangle method, whatever you want to do. But essentially, you'll see here that we have the origin here, okay, which is our initial point for basically everything, okay? So the 6 plus 5i, let's say you sketch that first. So here's the terminal point. Then you have this -9 plus 3i, okay? So if we sketch that guy, that's the terminal point. And then again, if you want to do the parallelogram method, this guy gets shifted down to make this side here, okay, to make this side here. This guy gets shifted down to make this side here, okay? And this point right here is going to be your terminal point for the resultant vector. You see you get the -3 plus 8i. Again, if you want to use the triangle method, you can do that as well. Basically, you're going to shift this guy down here. So you would have that vector going like that, okay? And you would have your triangle looking like that, okay? So whatever you want to do, you can just show this graphically. I prefer this method because this is what's shown in most textbooks. And basically, you're keeping in line with the fact that this is a position vector, and this is a position vector, and then this is your resultant vector. All right, so what we want to do now is move into writing a complex number in what's called the trigonometric form, also known as the polar form, okay? So typically, we see our complex numbers written as a plus bi, where again, the a is the real part and the b is the imaginary part, or some books will say bi is the imaginary part. So what we're going to do is just switch this over to the x plus yi, where x is now going to be the real part and y is going to be the imaginary part. Now, in terms of notation, you're going to sometimes see that the I is switched. So you might see x plus I times y. This is done for clarity. Sometimes you'll have a radical involved. So you just have to be very, very careful when you have I written like this to understand what the imaginary part is, okay? That I is always separate from that. You have to remember that. And I'll show you that specifically here with some examples. Now, in terms of getting this guy from what we call rectangular form, which is the form that you normally see it in, the a plus bi or the x plus yi, into this polar form, you need to consider a few things. So we've graphed this guy as a vector, a position vector to be specific. So the initial point is at the origin, 0, 0. The terminal point is at the complex number x plus yi, or you could say the coordinates here are x, y, okay, on the complex plane. So if you think about a few things, first off, the length or the magnitude of this vector is labeled as r. We've seen this a bunch of times where we think about, okay, well, the length of this guy is the absolute value of the complex number, okay? Going back, we said the absolute value of a plus bi is the square root of a squared plus b squared. Again, this is just the Pythagorean theorem, right? If I go through here and I think about how to get the length of this r or the magnitude of this vector, well, this guy here would be r squared is equal to the length of this, which is x, so x squared, plus the length of this, which is y, so y squared. A squared plus b squared equals c squared. We're just going back to the Pythagorean theorem. If I take the square root of each side, I get that r is equal to the square root of x squared plus y squared. Okay, so this is something we're going to need today. When we want to find our r value, we just use this little simple formula. Again, if you can't remember it, it's just the absolute value of the complex number. That's all it is. So let's go ahead and cut this away, and let's just paste this on this little sheet here. We'll just go back and forth. So we also need to know about a few other relationships. So we think about this angle theta here, this direction angle for our position vector. The cosine of theta is what? So the cosine of theta is what? Remember, it's adjacent, which is x, over hypotenuse, which is r. And then we can also say that the sine of theta is what? It's opposite, which is y, over hypotenuse, which is r. Okay, let's grab these and cut these away and paste these in here. Again, we're going to be using this in a second. And basically what I want to do is I want to solve these for x and y, okay? So to solve this for x, I would multiply both sides by r, and I would have x is equal to r times the cosine of theta. To solve this for y, I do the same thing. I'm going to multiply both sides by r, so I would have r times the sine of theta, okay? So we're going to use this in a little while. Let's go back up. There's one other thing we need. So we recall when we work with vectors, we figure out the direction angle theta using the tangent, right? So we say that the tangent of theta is equal to y over x, where x is not 0, okay? So we're going to use this as well. But again, you remember from working with vectors, you have to be really, really careful with the inverse tangent function, okay? With the inverse tangent function, you're going to get something in quadrant 1 or 4 only. 1 if your argument is positive, and 4 rotating clockwise if your argument is negative. So let's come in here and let's paste this in. And I guess we can put that about right there, okay? So the polar form, let me just start with the rectangular form. So we have x plus yi. If you want to write yourself a little note and say, okay, well, this is a plus bi, just to keep track of this. Again, x is the real part, just like a. Y is the imaginary part, just like b. Okay, that's all it is. Just a little notational change. So this is the standard form or the rectangular, I can never spell that, form, okay? Then if you want the polar form, we're going to do a little bit of work. So let me do this on another sheet, and I'll actually come back. So we have the x plus yi, and I'm just going to be plugging in for x and y. If I go back, you see that x is r times cosine of theta, and y is r times sine of theta. I'm just going to plug in. So r times cosine of theta will be plugged in for x, and r times sine of theta will be plugged in for y. So r times sine of theta, okay? So what I'm going to do here is say this is equal to, I'll have r times the cosine of theta. Then I'm going to put plus, I'm going to put r times sine of theta, and I'm going to wrap this in parentheses just for clarity. This is going to be multiplied by the imaginary unit I, okay? So again, this is x, this whole thing right here, and then this is y, this guy right here, and this multiplying the imaginary unit I, okay? So I'm going to go a step further and just factor the r out now. So let me put equals, and I'm going to come down here with this. Let me drag a little arrow down here. If I factored out the r, where would I be? I would have r times, inside of parentheses, I would have my cosine of this theta, and then plus, again, I pulled out the r, I would have my sine of theta, but what I'm going to do is I'm going to put the I out in front. So I times this sine of theta, okay? And you have to be very, very careful when I is written this way, because sometimes it's going to get mixed up. And again, I'll show you some examples where you need to be careful of this, okay? So this is your polar form. That's all it is. Some books will abbreviate this, and they will put R times CIS. It's an abbreviation. So the C, then you have the I, and then the S. Okay, so that's how you can remember. R times CIS, and then times the angle theta. Okay, so if you want to write it as R cis theta, or write it like this is more popular. This is your polar form. So let me write this up here. We have R times, you have your cosine of theta, plus I times your sine of theta like this. This is your polar form. Or again, some books are going to call this the trigonometric form. And the shorthand for this is R times CIS of theta. All right, let's just look at some examples of converting back and forth between the two. This is a very, very easy process, but you do need to work a few examples so you get used to things, okay? You'll also see a lot of these come up over and over again because they're using values on the unit circle. So what I have here is 2 multiplied by the cosine of 150 degrees plus I times the sine of 150 degrees. So this is in the polar form, right? You have some value R here, which in this case is 2. And it's multiplied by cosine of some angle theta, in this case is 150 degrees, plus I times your sine of some angle theta, okay? So all I would do here basically is figure out what is the cosine of 150 degrees, what is the sine of 150 degrees, basically replace things, and then use my distributive property to distribute the 2 into everything, and you're going to have it in the format of x plus yi, okay, just like you want. So first and foremost, what is the cosine of 150 degrees? Remember, this has a 30-degree reference angle, and we're in quadrant 2. Cosine is negative, okay? And the 30-degree reference angle, cosine of 30 degrees, is square root of 3 over 2. So I can say this is the negative of the square root of 3 over 2, okay? Then the sine of 150 degrees, same 30-degree reference angle, but again, I'm in quadrant 2, so sine is positive. This is going to be 1/2, okay? And positive 1/2 at that. So all I need to do now is just go through and basically replace things. Let me get rid of this. I think we don't need this anymore. I'll say that I have what? I'm just going to put equals here. I'll say 2 times. Here I'll put the negative of the square root of 3 over 2. And then plus, I'm going to put the I here, okay, times, I'll put my 1/2, okay? Be very careful with the I. Again, it gets switched around a lot. Sometimes it's here, sometimes it's there. Just be careful with it. So let's just erase this. We don't need it anymore. And now I'm going to distribute the 2 to each term inside the parentheses. So I would have 2 times the negative of the square root of 3 over 2, and then plus, I'll do 1/2 times 2, and then you can do times I, okay? So basically, we see that this would cancel with this, and this would cancel with this. And in my rectangular form, I have the negative of the square root of 3, basically plus 1I, or you could just say plus I, okay? So this is my rectangular form, or my standard form. And again, this right here is the polar form, or some people call this the trigonometric form. All right, let's look at another one. So we have the polar form here. We have 6 times. You have the cosine of 135 degrees plus I times the sine of 135 degrees. So what is the cosine of 135 degrees? So again, you're in quadrant 2, so this is negative. what is the sine of 135 degrees? Again, you're in quadrant 2, so this is positive. Remember, 135 degrees, you have a 45-degree reference angle. So in each case, you're going to have square root of 2 over 2, right? This guy is just going to be negative because cosine, again, is negative in quadrant 2. And this guy would be positive, okay? So basically, I could replace this and say I have 6 times. This is going to be the negative of the square root of 2 over 2. And then plus I times, you're going to have the square root of 2 over 2, okay? So if I distribute the 6 into each term, I would have 6 times the negative of the square root of 2 over 2 plus I times, let me go ahead and switch the order here so this makes more sense. We'd have the square root of 2 over 2 times 6 and times I. And I'll just go ahead and cancel this. This cancels with this and gives me a 3. This cancels with this and gives me a 3. So basically I'm going to have the negative of 3 times the square root of 2. And then plus you'll have 3 times the square root of 2 and then times I. Now again, a lot of times for clarity, you're going to move this around. Let me drag this down here so that's a little bit better so you can see things. I'll erase that and put that back in. Instead of having the I here, most books will do 3I like this, then times the square root of 2. This is just to make it completely clear that the I is not under the square root symbol. Okay, so the rectangular form here, or again the standard form, is negative 3 times square root of 2 plus 3I times square root of 2. And then again, your polar form, or the trigonometric form, is going to be 6 times this quantity, cosine of 135 degrees, plus I times sine of 135 degrees. All right, let's look at something more tedious now. So we're going to convert from our rectangular form to the polar form. I'm going to give you 3 easy steps for this. The first thing that I always do is I figure out what quadrant my complex number is in. You can do that by just thinking about the real part and the imaginary part. So in other words, if you were to graph this, again, on the complex plane, it's A comma B. So if this is positive and this is positive, then you're in quadrant 1. Okay, if this is negative and this is positive, I'm going left and then up, so I'm in quadrant 2. Okay, if they're both negative, I'm in quadrant 3, right? I'm going left and then down. And then lastly, if this is positive and this is negative, well, I'm going to be in quadrant 4, right? Because I'm going to the right and I'm going down. So just think about your real part and your imaginary part and ask yourself the question, if I was to graph this as a vector, okay, where would I be? Am I in quadrant 1, 2, 3, or 4? Okay, so that's the first thing you want to do. Now, if I look at this guy right here, I have 2 minus 2i times square root of 3. Again, this I is here for clarity. Okay, if you want to, you can write this as 2 minus 2 times square root of 3 times I. So it's crystal clear that this part right here is the real part, and this part right here, you can go ahead and take the negative with it, is the imaginary part, right? So A plus BI. Okay, so we know that the real part is 2, so that's positive. The imaginary part is negative 2 times square root of 3, that's negative. So I'm going to the right, okay, and then I'm going down. That means I'm going to be in quadrant 4, right? Because again, this is positive and this is negative, and you're thinking about this in terms of the complex plane. Okay, so now I know that theta is in quadrant 4. We need that for later on when we're getting our angle theta. So if we want to get this trigonometric form or the polar form, it's r times cosine of theta plus I times the sine of theta, okay? That's all it is. So I need to figure out what r is, and I need to figure out what theta is, and I'm done. So how do I figure out what r is? R, again, is just the absolute value of the complex number. Okay, we've been doing this forever. It's the square root of the real part squared, so 2 squared, plus the imaginary part. Again, if you're writing it like this, it's crystal clear. Negative 2 times square root of 3. So negative 2 times square root of 3, okay, this guy being squared. Some students make a mistake when it's written like this. Again, they put I in there for some reason. Again, just go ahead and write it like this so it's crystal clear that this is the imaginary part. You want the a squared plus the b squared, or the x squared plus the y squared, whatever the notation is, okay? The real part squared plus the imaginary part squared, okay? That's what you want. So we have r is equal to the square root of, this is 4, and then basically you have negative 2 squared, which is 4, and you have square root of 3 squared, which is 3. So 4 times 3 is 12. So I'd put plus 12 here, okay? So r is equal to the square root of 16, so r is equal to 4, okay? So the first part of that, okay, the first part of that is done. So r is equal to 4. And this looks like I made a radical here. I was just making a border. So let me kind of clarify that and put this maybe like this or something. That would be better, I think. And maybe I can just do it upside down. I'm just trying to make a border. That's not a radical. So r equals 4. Okay, so now I need to find theta. So what is that going to be? Again, you use the fact that the tangent of theta is y, okay, or the imaginary part, over x, or the real part, okay? So the imaginary part, you have your negative 2 times square root of 3 over your real part, which is 2, okay? So you can go ahead and cancel this with this, and this is the negative of the square root of 3, okay? Now what I would do, okay, is not punch this into the calculator as the tangent inverse of negative square root of 3, because you're going to get something in quadrant 4 rotating clockwise. Now, your teacher may allow that as an answer, but typically you want something between 0 and 2 pi, where 0 is included and the 2 pi is not, okay? So what I'm going to do is I'm going to say that I want the tangent inverse of the square root of 3. And this is going to give me 60 degrees, okay? This is going to be my reference angle, and I'm going to be in quadrant 4, okay? Remember, we figured out we're in quadrant 4 for this reason. So in quadrant 4, if I had an angle with a reference angle of 60 degrees, to find that I would do 360 degrees minus 60 degrees, which gives me 300 degrees, or in terms of radians, it would be 5 pi over 3. So now that we've done all this work, okay, we are ready to write this guy in polar form. And I guess you can get rid of this. We don't really need it anymore. I'm just going to write this and say that basically this guy, and I'll just even erase this, would be the r, which is 4, times you would have cosine of your angle. So you can use either one you want. You can do it in radians or degrees. So 300 degrees. Then plus, again, I'm going to put I first, and then times your sine, okay, of that same angle, 300 degrees. If you want to write this with radians, all it is, I'll put equals again, so 4 times, you're going to do cosine of 5 pi over 3, okay, and then plus I times the sine of 5 pi over 3. So always go with what your teacher says. If they want radians or degrees, just ask them, okay? So we basically have this done, and also if you wanted to, you can use that little abbreviation. Let me just show you that real quick. You could do, this is 4 times CIS. So again, the C, the I, and the S, that's where the abbreviation is coming from. And then times, let's just go ahead and say 5 pi over 3. All right, let's look at another example. So we have negative 2 times square root of 3 minus 2i. So again, the first thing you want to do is figure out what quadrant is theta going to be in. And again, you can speed this up at this point. Again, here's the real part. It's going to be negative. Here's the imaginary part. It's going to be negative as well. In other words, if you were to graph this, you would have negative 2 times square root of 3. This would be your location on the real axis. And then you would have negative 2. That'd be your location on the imaginary axis. So in other words, this is negative and this is negative. So I know I'm going to the left and down. So I'm going to be in quadrant 3. And I put equals here. I should just put is in quadrant 3. Okay, so we can keep that straight. Now, what I want to do is quickly find my value for r. I'm just going to make that a little bit more clean. So my quadrant 3, I'll just put for my angle theta. So for r, again, it's the absolute value of this complex number. However you remember it, remember it's the square root of the real part squared plus the imaginary part squared, however they're giving that to you, okay? So I'm going to take the square root of, I'll take negative 2 times the square root of 3 being squared, then plus I'll have my negative 2 being squared, okay? So from here, I know that basically negative 2 squared is 4, square root of 3 squared is 3. So 4 times 3 would be 12. And again, we already know this, so this is going to end up being 4, right? Because this is 12 plus 4, that's going to be 16. Square root of 16 is 4, right? But to go through the steps, this would be 4. Again, 12 plus 4 is 16. Square root of 16 is going to be 4. So r is 4, we know that. So let's find theta. This is the one that takes a little bit longer. So we know that tangent of theta, again, is y over x, or you could say b over a if you think about this in terms of the traditional way we think about complex numbers. It's going to be the imaginary part over the real part. So the imaginary part is negative 2, so negative 2, and the real part is negative 2 times square root of 3. Okay, so this is going to cancel, and I'll have 1 over the square root of 3. If I rationalize the denominator there, so times the square root of 3 over the square root of 3, this is the square root of 3 over 3, okay? So basically, if I punched up the inverse tangent of square root of 3 over 3, I'm going to get something in quadrant 1. Remember, I'm looking for something in quadrant 3, okay? So let's go ahead and set this up. I want to go inverse tangent, okay, inverse tangent of square root of 3 over 3 like this. So you hit that up on your calculator, you're going to get 30 degrees, okay? And again, in quadrant 3, if I have an angle with a reference angle of 30 degrees, to find that, I would do 180 degrees plus 30 degrees, okay, which would give me 210 degrees. So theta is going to be 210 degrees. So now that we have all the required information, I can just put equals. I'm going to take my r value, which is 4, and I'm going to multiply by, again, you have your cosine of this angle, 210 degrees, plus I times the sine of this angle, which is 210 degrees. So that's basically it. That's your polar form. Now, if you want to write this with radians or write it as an abbreviation, you can keep putting equals. So 210 degrees in terms of radians would be 7 pi over 6. So you could say this is 4 times, you'd have the cosine of 7 pi over 6, plus I times the sine of 7 pi over 6. And again, one more time, this C, this I, and this S, you can use it to abbreviate. So you could say this is 4, and you go CIS or CIS, and then you'll say your angle. So again, you could do degrees or radians, whatever. We'll do 7 pi over 6. So another way to write it, this is the shorthand. All right, let's look at one more example. So we have the negative of the square root of 31 over 2 plus the square root of 93 over 2 times I. Again, just be careful. Sometimes they'll put the I up here because you're working with a radical. Just be able to separate the imaginary part from the real part. Okay, you need to know what those are, and you need to not get I mixed into that. Okay, so what I'm going to do here again is think about what quadrant am I going to be in. Okay, this is negative, this is positive, so I'm going to the left and I'm going up, right? So I'm in quadrant 2. So theta is in quadrant 2. Okay, very important to understand where I am. Now, once I understand that I'm in quadrant 2, again, when I go to find theta, okay, I'm going to basically get a reference angle and then use that in quadrant 2. Well, let's find r first because that's a little bit easier. So r equals, again, the square root of, take your real part being squared. So negative of square root of 31 over 2. We're going to square that, plus take this guy, the imaginary part, so the square root of 93 over 2, this guy squared. So r is equal to what? If I square this, I'm going to get 31 over 4. So the square root of, you'll have 31 over 4, plus this guy would be 93 over 4, okay? If you add those together, you're going to get 124 over 4. So 124 over 4, if you make that division, you're going to get 31, okay? You can't simplify that. 31 is a prime number. So basically, r is just the square root of 31, okay? So r is equal to the square root of 31. Okay, let's work with theta now. So the tangent of theta is what? It's the imaginary part, or y, or b, however you want to think about it. So square root of 93 over 2 over the real part, which is x, or basically a, however you want to think about that. I'm just going to flip this guy, because when you divide fractions, you multiply by the reciprocal. So I'll put the negative of 2 over the square root of 31. That's going to allow me to cancel this with this. I know that from the quotient rule for radicals, I can divide here. So 93 divided by 31 is 3. So I can basically say this is the negative, okay, the negative of the square root of 3. Now, we know from the first example, this guy is going to have a reference angle of 60 degrees. If I did the inverse tangent of square root of 3, I'm going to get 60 degrees. So because I'm in quadrant 2, what I want to do is I want to take 180 degrees, and I want to subtract the reference angle of 60 degrees, and that's going to get me to 120 degrees. So theta is 120 degrees here. Okay, so theta is 120 degrees, or in terms of radians, you could say this is 2 pi over 3. Okay, so basically I'm ready to set this up. I can go ahead and say this equals, and let me just drag this out of the way. Put this down here. I'll say my r value, which is the square root of 31, times, let's just go ahead and use degrees first. So I'll say cosine of 120 degrees plus I times the sine of 120 degrees, okay? And again, you can keep going, right? So if you want to put this in terms of radians, I'll put equals, I'll do square root of 31 times the cosine of 2 pi over 3, and then plus I times, we'll do the sine of 2 pi over 3, okay, like this. And lastly, if you want to do your abbreviation, take your r value, which is square root of 31, and then times that CIS, or the CIS, again, the C, the I, and the S. So CIS, that's how you can remember that, and then times your 120 degrees.